Ma'am, shall we start, ma'am?
Can start.
Okay. Very good afternoon to all the participants. On behalf of PhD College of Technology, Department of Tripoli, and AICT Atal, I welcome the speaker of today's afternoon, with Uma Maheshwari, to deliver the topic on EMI-EMC issues in power converters. To brief about her, Uma Maheshwari is a technology manager at Pramura Software Private Limited, Coimbatore. She has around 19 years of industrial experience. She completed a graduate program in electrical and electronics engineering at Amrita College of Engineering, Coimbatore, and a postgraduate program in embedded systems and technologies at Anna University, Coimbatore. She has authored 2 books in the area of electronics and PCB simulation, published by Cambridge University Press, London, and Xavier, UK. We welcome you, ma'am. I hand over the session to you.
Thank you, Dr. Archana.
Thank you, ma'am.
I think my voice is audible with
Yes,
all,
ma'am.
and my screen is visible with everyone.
Yes, ma'am. Yes, ma'am.
Okay. I am not in a position to share my presentation at this time, so participants can take the notes.
Okay.
So with this note, I welcome you for this presentation. So I'll share my knowledge to you on EMI EMC issues in power converters, electric vehicles, and smart grid to all of you. So thank you for this session. So shall we
Thank
begin
you.
the session?
Yes.
Okay. So at this thing, I would like to introduce the EMI. It is overview of EMI EMC and EMI EMC aspects of electrical systems for vehicles. EMI in power electronics, or in terms of power converters or smart grids, whatever it may be. Design strategies to be followed to the abstract level, and EMI-EMC measurement and testing to be done in the final product. So, as you all from the research and academic thing, so EMI-EMC is I don't think it is a part of the syllabus. So it may be useful for you. I'll for you to understand and how the product development life cycle goes. It can be applied to your research work or project works, whatever it may be. So I'll start with the basic introduction of the EMI EMC. So here, what is EMI? EMI is an electromagnetic interference. It refers to the unintentional electromagnetic emissions from the electronic gadgets or a product, whatever it may be. There may be an intentional EMI. This may be intentional. Maybe this is it's actually a specific purpose. It can be to confuse or damage the terrorist or enemy countries. Like it can be handled as a weapon. So here we are in this complete session. We are going to concentrate on unintended emission. That is from the electronic circuits or electronic components, which is happening unintended. So that is going to see. So intentional EMI also has some other advantages or disadvantages. So we are leaving out that here. Then coming to EMS is electromagnetic susceptibility. That is immunity of the system to perform in the presence of electromagnetic interference. So how well it works, how it can perform its actual functionality is the susceptibility. So combination of EMS and EMI is put together called EMC, that is electromagnetic compatibility. This is a cumulative assessment of EMI and EMS. So as we know, we have in and around all electronic gadgets, which is running at a high speed. For example, laptops, mobile phones, cellular tower, and high transmission and distribution lines. We have in household electronic gadgets. So all, with knowingly or unknowingly, all have the electromagnetic waves in and around it. So some of the products might have under comes under regulation, so some may not be. If you see, if you purchase for example, if you purchase a cell phone which functions, iPhone functions same as the normal low cost mobile. So but the difference is the EMI-EMC uh, uh, criteria. So that is the regulation, the certification, all comes under it. So it takes around some cost issues. So it's a trade-off. So for any product, any industrial product or any IoT product or any research product, this life cycle goes like this. So we need to define the clear product specifications. So without product specifications or brainstorming sessions, you cannot proceed with the completion of the product. So we need to have the clear specifications, and we need to start with some R&D work. So we have to select the component. We need to input, output. What is the input? What is the output? And what is needed for the processing thing? So which component to be used? Whether it is a compliance with EMI or EMC. So like that, we need to start with some R&D work and have the product creation created. And we need to, after development, we need to create with the prototype or a field. We have prototype. With the prototype, you need to have the field test, and after that, definitely it has to be done for the EMI test. And if the results wave fluctuates, we need to mitigate the EMI or EMC in the design stage itself. So this loops goes on like this. After that, after the result is okay, we need to give for the regulatory certification process and produce the samples, or produce the mass production, and it has to be, it will go for the selling mode. So will, what causes the, what will cause in the presence of EMI? So it will be the complete malfunction. It will not perform the desired output. So that is the one thing. So degradation of the performance. So efficiency of the performance may be low, or any required output cannot be achieved through the EMI thing, or maybe some delay. So whatever it may be, some degradation of the performance can happen. And maybe a complete failure of another system, because of the one system complete of the another complete failure of the another system can happen, which is working close to the same environment. So we can we have many classifications of EMI. So based on the source, it can be two: man-made or natural. So man-made is actually intentional transmission line made by the man through televisions or videos or radars, like that. So natural source can be cosmic noise, lightning, electrostatic discharge, like that. So based on the interference, period of interference, it can have continuous interference or impulse interference. Continuous means, as the name itself indicates, the continuous signal generates. So impulse is a high surge like thing, so burst like thing. So it can be it can cause switching action, lightning on ESD related to thing. So based on the bandwidth, we can have narrow band or broadband. So narrow band has the signal frequency which is very narrow. So it is opposite to the broadband. So broadband or EMIs are generated mainly by the man-made actions such as arc welding, natural resources, and like that. So this slide explains the main events of the EMI issues. The thing is, there are three main parts of the EMI events are the source and victim, and in between the transmission line path. So the transmission path can be either conductive or radiative. So conductive side. So there are four ways of coupling can happen. So one is common impedance, that is low impedance level, and through the electric fields, that is capacitive induction, and through the magnetic induction, and both the electromagnetic waves. So radiation can happen in the air. This is actually the inductive coupling. This is the capacitive coupling. So the both conductive and radiative emissions from the source, which affects the victim. Victim is the affected part. This may be a victim, may be a electronic gadget or a person. So coming to the conductor interference, as we discussed, it is the signal propagates through a metallic conductor, or this may be in the case of PCB, it is a traces, or in the case of normal thing, it is a wire. So it is a through contact in the direct interference, it can happen. So this is by means of capacitors or inductors, transformers, etc. So radiated interference means that it is not it is an indirect interference that is transferred through a medium by an electromagnetic field. So the electromagnetic radiation escapes from the source to the victim and spreads out in the air or space according to the law of wave propagation. So this is actually a little more explanatory slide. So here the emitter is a source, the susceptor is a victim. So you can see the coupling path. That is, coupling path is a conduction or metallic path. So coupling can happen between emitter and susceptor through conduction or radiation. So radiation is a non-metallic path. So at the emitter side, we have radiated emission, and conduction side at the emitter is conducted emission. So here at the susceptor side, we need to take care of the immunity part. So radiated susceptibility has to be taken care, and conducted susceptibility has to be taken care. So at the emitter sides, some of the components that emits the emission, that is radiated or conducted emission, are transmitters, high speed logic, high frequency generators, power switches, inductive loads, ESD, and lightning. And at the susceptor side, we have receivers, analog circuits, digital circuits, of course, human beings. So these two have the high unwanted emissions and low susceptibility threshold. So for this, we have to have the clear design strategies and design plan and testing, and especially EMI-EMS regulation has to be followed to protect the environment and the functionality of the functionality and life of the product. So there can be two modes of conduction can takes place. One is common mode. This is a basic thing. So differential mode. So under the common mode, the current goes like this in the same direction. The differential mode, the return path will be the different direction. So coming to the power converters or power electronics, so wherever we see the automotive or any industry or any high sophisticated applications, we have definitely a power electronic circuits. So with the power electronic circuits or power converter circuits, the three major issues are losses, EMI, harmonics. So if because of the losses or these three issues, it's directly proportional to the size, cost, and efficiency and quality of the product. So it has to be taken care in the product level itself. This slide shows a typical power electronic system block diagram. So we have before converters, we need to have some filter, and after power converter also we need to put some filter. And finally, the load, it can be, in the case of uh, smart vehicles, uh, from the load, the feedback control should be taken to the controller. This depends on the application. So feedback signal can be given to the controller for the controlling the signals to the power converter. Depends on the application. So I'm just putting after the filter this feedback control in this situation. So anyway, we need before and after the power converter, that is filter, filter EMI filter or output side LC filter is required to mitigate these issues. So generally, the power electronic is power circuit plus electronic circuit we can call. So power circuit is that converts unregulated input power waveforms, that is power AC or DC type, and two regulated DC voltage or current and delivers it to the load. And electronic circuits, that is converter, that controls by measuring the input and output voltages, input output current or current, and generate signals to the power circuit. So this is the base of this power electronic circuits. So power circuit has these are all the components: capacitors, magnetic elements, and transistors in a switched mode. Definitely, the fast switching will be the problem. That is the source of the magnetic noise. So here, converter may also emit the high frequency electromagnetic noise and upset near field as well as the far field coupling. Now, the research targets in power electronics. In the current scenario, research trends are analysis of the electromagnetic emission by measurements, modeling, and simulations. Of course, in the filter side is the external filter. These are all in the internal side. So filters also development of active EMI filters also in the high power converters to suppress the EMI noise is a recent research targets. So coming to the power electronic application, so wherever we see, as discussed, wherever we see there will be a power electronics components will be sitting there. So for example, right from the small electronic circuits like tiny iPods, cell phones, or based on switch mode or PDM converters, like, and as well as the industry side DC motor to vary the speed and performance of the things of DC motors such as train, electric vehicles, industrial use, all industrial uses. There will be a power electronic applications. The power like we in the current case we have the smart grid and electric vehicles. So there will be definitely a power electronic components will be present there. And what does the power switches does? So powers actually in the ideal scenario, the voltage across the switches should be zero and current leakage current should be zero. So actually in the ideal scenario will not happen in the practical side. So there will be some deviations in the thing. So that component will be dV by dt and di by dt. So it has to be minimized. So for the switches, we will use pulse width modulation technique. So pulse width modulation, that synthesized, the signals of pulse width modulation signal is synthesized and transferred to the switches. That may be a gate drives or whatever it may be, switches. So that switches will have there will have the dV by dt and di by dt components. So these phenomena depends on the several issues such as characteristics of that affects the power switches, controls, gate drives, stray parameters, and operating points of the system. So main issues of these power switches, as already discussed in the losses, EMI, and harmonics. So losses due to mainly in the conduction and switching losses, or stray component losses, or losses in the controller. So this has to be mitigated or identified in the initial stage itself, design stage itself. So coming to the major issues of EMI. So as discussed, there are two main sources of the EMI power, dV by dt and di by dt components during switching times. So high di by dt may create over voltage in the power converters. So high dV by dt component create leakage current in the magnetic elements. So this has to be reduced. So how to reduce? By increasing the switching time, but it indirectly increases the losses. So there is a trade-off between the designers has to decide which has to be given preference and which has to be done correctly with the without affecting the functionality. So other alternative is to reduce the stray inductance and capacitance of the system, and by using the better layout and better interconnections, interface configurations, etc. So third one is harmonics. Again, it is increasing switching frequency can reduce the lower order harmonics. Again, that harmonics also has to be mitigated, but switching losses are increased if we give the thing. So it is again trade-off between quality and losses. So this is the thing, how EMI expert can help at the first in the design stages. So we have to have the clear dV by dt component and di by dt component, and with the switching frequency, how we can achieve it without with suppressed EMI and minimize losses. So these are all the challenges in the design of modern power electronic systems, that is power converter smart gate. So understanding the EMI issues in the power converter side. So analyzing the switching transient in the transient is actually a sudden burst at the load side. I mean power line side. So that has to be analyzed in the switching area. And in the beginning stage itself, EMI we need to consider the EMI of the thing designs areas. So selecting a proper topology of the PWM techniques, and low capacity couplings may be a good design magnetic element such as inductors, like we have to integrate with the circuits. So low stray inductance, that also it's a challenge of the power electronic circuits. So coming to the vehicle electronics, so smart vehicle electronic systems may helps a lot. For example, keeping the distance of the vehicle and automatically parking with the space within the space, and warning us in case of danger situations like ABS solutions. Like there are many situations like this. So this happens only when the electronic control unit ECU functions well. Otherwise, it will not perform these operations. So and other side, critical errors need to be detected at the right time. There should be any time delay for the error reduction. Otherwise, it will affect the accident. It will end up with the accidents. So. So in the automotive and vehicle electronics, we have the EMI problems such as integration of smart power devices with the control units, and some safety critical applications such as airbag control. We need to have clear clear low level EMI with the specified standards, product standards. So and system clock speeds as we are using very high controllers like microcontrollers, microprocessors and all. So there will be clock speeds and very high frequency signals are used. So there definitely we will be the switching noises there present there. So vehicle electronics are affected with several factors. Suppose it is parked in a harsh environment. High reliability. So we need to test the reliability before the thing. So if it is not reliable, so it will perform as malfunction. So extreme cost sensitivity. Definitely it will involve the cost. So these are all the several factors that affects the vehicle electronics. So what are the threats? EMI threats that are faced in the vehicle electronics are susceptibility and emissions. So emission side we need to, the source side we need to control, susceptibility side we need to put some immunity systems. So I have, on this slide we'll see some of the accidents happened because of the EMI problems in the automotive industry. So in the year 2012, Chrysler forced callback all this particular series of vehicles because of the EMI failure. That is due to the transient electrical spikes on the ORC module. That what happened is that triggered unintentionally of the airbags. So that is an accident. That because of that many loss happened to the company. So in the year 2013, Toyota had to recall more than 1 million vehicles of some series because of the EMI issues. That is mainly because of the ASICs airbag and unit control. And the year of 2015, Mitsubishi also had a callback, and so more than 550,000 vehicles for the EMI problems inside the electronic control module because of the lightning control, and it didn't work well because of the EMI issues. So might be the testing standards they might not followed correctly, or might have changed, or various reasons will be there. So most of the problems can happen. Jamming, suppose if what if jamming of a radio receiver happens for the police and fire and ambulance. So the life will be threatened because of this EMI issues. These are all the known problems. There may be unknown problems which we could not studied or come out there as a news. So testing and measuring the EMI is very important for the device functionality as well as the human beings. And so for that main source can be IC in the vehicle electronics, IC and ECU, that is electronic control unit. That has to be taken care by the car manufacturers or vehicle manufacturers. Of course, environmental condition also might lead to functionality failures that has to be taken care. So then human beings are put into risk if it is not valid correctly. So we'll see some of the threats in detail due to the EMI susceptibility. Uh, so that is mainly power transients and radio frequency RFI, radio frequency interference, electrostatic discharge, and due to the power line, that is electric and magnetic fields. We'll see about the power transients. So power transients is actually, as I already discussed, momentary burst of energy. That is a high energy which is induced upon the power lines. So which is very dangerous to the gadgets. So again, this is actually not only applicable for the automotive and smart grid vehicle area. This is common. This EMI-EMC is common for all the commercial and medical and all other electronic side. It is common for the team. So you can apply for your if you are in a power electronics project, you can apply these things to the thing. And if you are designing in the high speed PCB design, you can apply the similar things with the thing. So it's a general terminology for the power for what I am discussing here. So because of the transients, it can damage or upset the electronic system, as already discussed. So electronic devices become faster, it will become more vulnerable to the transient spikes. So it has to be taken care. So we'll see how we can take care in the later slides. So we'll just first analyze the what are all the threats are need to be or present in the scenario. So second is radio frequency immunity. Here the radio transmitters produces the thing. That is, if you are in the airport radar systems has radio emptying the radio signals for the for controlling the aircrafts. So if we switch on the electronic gadgets at the time land off or take off times, so it will have the confusion between the signals. So it may happen, because of the accidents can happen because of this. So this is the we need to have the immunity, perfect immunity for this thing. And not only the high speed signals, the low level, low frequency analog signals such as sensors are also most vulnerable to the RF frequency emissions. So voltage regulators also it has to be taken care. When using the only thing, if you are using, suppose if a simple board, you can use a single layer board PCB. So if you are using two layer board, it will the better results can be seen because of the shielding purpose. Because of the shielding of the signals, you can see the performance improvement in the thing. So in vehicles, uh, local onboard transmitter is useful, is as a, vulnerable to the or radio frequency threat. So the third is electrostatic discharge. There is actually an imbalance between negative and positive charges. Uh, this is humans are the main source of the ESD. So if a human with high ESD who assembles the product, and the charge will be transferred to the thing. So if you the immunity has to be taken by the industry for the ESD. This will cause, actually the direct or indirect effects are more with the ESD effects. So with a minimal, very low nanoseconds, there will be a very high rapid rise time will be there for the ESD current. So it has to be taken care. Otherwise, it will end up with the accidents. These effects can be observed up to 20 feet away. This is proved in the research. So you can see this waveform. So in the particular 1 nanoseconds, human body is gaining 10 amps current. So imagine how this affects the thing. So proper grounding is one of the solution for this ESD thing. The fourth threat is power line fields. So since a vehicle can go anywhere, under the power lines, or in any vulnerable conditions or harsh environments, it has to be taken care. So normally 50 or 60 hertz electronic gadgets, like electronic appliances will no longer have this effect. But at a low level analog circuits, like circuits can be affected with this magnetic field or electric field. So thus the power line requirements has to be taken care. So this is a diagram which shows the electronics presence in the automotive side. Almost all the things has a centralized control, so which controls all the automotive things, like lightings and door side, and regenerative brake systems, high voltage wire harness, like all the things are in the automotive electronic modules. So this is a typical block diagram which shows the power electronic side in the vehicle industries or things. So we have the temperature sensor, which that block senses the temperature, an ESD protection unit, and reverse battery protection, power clamp, gate controller drivers, open load detection and load current sensors, and overall control logic. So this has this altogether, which diagnostic functions, and does the diagnostic functions and the protection functions. So what it diagnoses? High pressure load current extends the high precision load current, and it senses the short circuit to the ground, and over temperature sensing, thermal shutdown indication, open load reduction, and power limitations indications, and load or short to ground reductions. So overload or short to ground reduction, it can diagnose. and the diagnosed things has to be protected uh, as this way. The load current limitations, it has to be done, and short circuit protection, over temperature shutdown, over voltage protection, under voltage shutdown, reverse battery protection, fast inductive energy demagnetization. Of course, electrostatic discharge protection has to be done. So these are all, and etc. These are all happening in the ECU, that is in the vehicle electronics. So some of the standards we, as discussed, in the automotive industry, ISO 26262 that defines the safety and protection functionality of the automotive components. So and apart from that, for the magnetic emission and electromagnetic immunity is defined by CISPO 25 or ISO 11452. So EMI, okay. Till now we have seen the basics and what will happen, or what are the things are going under the electromagnetic interference of the power converters or power electronic system. So from this slide, we are going to see in detail of design side. That is how the design can happen, and how we can measure, how we can test, like that. So under the design of EMI strategies, we can have some different approaches. So first is transient protection on all modules, that is for input lines. Secondary protection, like, such as filters, can be used in the filter circuit level. So, and after that, high frequency filtering on cable sides, because cables are the very good perfect antennas, which causes the EMI problems. So cable has to be taken care. So careful circuit layout has to be done. PCB layout has to be designed carefully, and cable and module shielding has to be uh, done properly, and local filtering, local coupling of things, and even shielding. The local shielding of most of the critical circuits has to be done perfectly. So coming to the design strategies under the ICs, we need to, either we need to suppress at the source or harden at the victim side. So the EMI problem. So to this is in the IC level, we can turn off certain high speed lines, which is not needed, which is not necessary. So otherwise, it will take some time which for the switching, or for another consecutive operations. So we need to turn off some of the unnecessary control signals. So you have care should be taken in on the clock drivers side. So main thing at the PCB side, or this is a major area where we can anyway we need to put some filters in the outside. So apart from that, in the PCB itself, we can have some we can follow some design strategies to mitigate the EMI issues. So these are the 7 points we can follow. We will discuss in detail uh, the subsequent slides. So first one is the most important one, that is identification of the most critical circuits of the schematic. So of your product thing. So then plan your board layout well, and appropriate board type has to be selected. So isolate with care, and decoupling of the power side, and bulletproof the interfaces, and consider multi-layer boards, and allow for plenty of filtering and decoupling in initial designs. So this will have some approximately 80% of the things will be solved in the things itself. So this is some application of the filter in the both sides, that is either source side or the victim side, uh, is is far better than if you follow the design at the PCB level itself. So some of the things we will see in detail. So identification of most critical circuits. Critical circuits here means the clock signals, address enables, and high speed data buses, we need to identify where it is being connected or routed. So this just adding a ferrite bead or small resistor in series with the clock is enough to mitigate this issue. It will have the better performance. So to match, this actually provides the better impedance match. Then of course, the microcontroller is a switching device. It is a again the source of the thing. So we have to have the proper. We need to identify which microcontroller and what it is switching speed, everything. And after that, minimize the clock runs and keep the clock traces and signals, crystal signals away from the connectors. That is very important because it will interfere. And then we need to identify, reset, interrupt, and control lines. High frequency filtering, such as small capacitors like 5 0 0 1 microfarad or farad beads will play a major role in the mitigation of it. So we can imply that. And small capacitors and farad beads or resistors are very effective filtering against spike and transients. And second, plan your board layout. So for under the board layout, we can have in the design stage itself we can plan how this board layout has to be done to mitigate the EMI problem issues. So for example, the proximity levels of the components, what components has to be placed, where to be placed, and all these things we have to be very particularly analyzed in the circuit diagram itself, and grouping the circuits by the speed of operations. So that will also have the major impact on that. The special care with the input and output circuits has to be taken into account. So cables still act as antennas on the high frequency side. So it has to be taken there. So this slide shows the proper layout and the backward layout. That is, we have seen the poor layout. So all the signals, it is noisy signals, that is high speed. The red colors are high speed, and this is a low speed. So these are mixed together. So here, in the good layout, the high-speed digital signals and analog signals are separated, and power supply is separated, and clocks is separated. So this will be the good strategy to follow while designing the PCB itself to mitigate it. EMI and the PCB. Then again, the selecting appropriate board type of the board also it plays as a major role. So if you design the PCB with a single layer is far different from the double layer. Maybe a cost can include in the double layer board, but definitely it will be a solution for the EMI problem. So because of the space constraints, you might have used loops to connect the components. So this can be avoided if you have the multi-layer, that is 2-layer board or 4-layer board type. So and you'll have some enough space to shield the traces, shield the connections. That is, you can pour some ground fields which act as a low impedance path for the return current, and definitely the impedance will be lower because of this. So and one more point is this will definitely minimize the crosstalks between traces. As the 2-layer board, we have many space, single layer compared to the single layer. So 2 layers you can use for the connection of the things. So this actually a trace is a cross section of the PCB. This is actually a trace. So because of the space you have, this signal is not coupled with the neighboring signal. Here, in case of single layer, if you don't have the space, you have to do the trace connections very closer to the neighboring trace. So you'll have the coupling. So because of this, the crosstalk definitely occurs. So for your understanding, I just show the 6-layer of the cross section piece of the PCB. So this is the top layer. If the top layer doesn't have the enough space, we can take the connections in the middle layers, that is 2 3 4 layers, and of course the bottom layer. So uh, this will have the enough space to reduce the crosstalk in case of high speed signals. This only happens in the high speed signal. So in case of low speed signal, that is not necessary. If the EMI also will not be that much problematic thing. So you can use single layer is enough. But in case of high speed signal, like automotive industries, automotive high speed, high efficient PCBs has to be taken care with the multi layer. And isolation with care should be taken. So most of the planes are aligned. So internal power and ground are here in the PCB. We call it as plane layers. So these planes has to be aligned properly, and signal and power interface between the isolated areas. So isolated with the ferrite and inductors, and it has these components should be isolated between the among them. So and route over the appropriate return plane. So has to be the traces has to be connected through the return path has to be done. Return path of the current has to be taken care in case of high frequency signal. Otherwise, it will definitely it will create a EMI issues. So in case of this shows the driver and receiver side. Here the current driver see the current direction goes like this. So the return path of the current closes the circuit as like this. Actually second layer is actually ground layer. So this is the first layer and second layer. The second under the second layer only through the ground the return current goes like this. So it will take the shortest path of the thing. Where in case of high frequency, it will not take the shortest path. It will take only the longest path. That is trace, and under this only it will take the under this trace only take the longest path. So in case of any discontinuity in the ground plane, then the second layer means the second layer, it will affect the return current. So that will affect the board performance definitely, and it will cause the signal integrity as well as the EMI problem. So for any electronic thing in the low frequency, it acts as an ideal thing. For example, I have shown only for the wire. So in case of resistor, it may be different. In case of capacitors or any component, it may be a different in the coming to the equivalent part. So in wire acts as a low resistance in case of low frequency, but L component also includes in case of high frequency. So before designing the circuit, we have to think with which frequency the circuit operates and what will be the equivalent circuit has to be designed to model in the software tools. So this idea of the equivalent circuit has to be important. Again, the fifth point is the decoupling the power. Decoupling of the power definitely radiated emissions are caused the poor decoupling. So we have to have the either 0.1 microfarad or 0.001 microfarad has to be applied for proximity to the controller or high frequency components. So these are simple capacitors can play a major role. So or in the power side, we can have inserting a simple ferrite with series with the VCC line is enough for this thing. So this improves the signal integrity as well. So the small LC filter further isolates the LC filter can be applied. That is which isolates the VCC traces from the current demands of the switch device. So every integrated circuit has to be decoupled. So that is the main point which I am going to stress here. And bulletproof of the interface we saw. So we have filter at your power and ground connections in the module side itself. And we have power interface, signal interface. So the power interface and the high frequency protection in the input lines are just by applying the few high frequency capacitors is enough. In case of signal interface, a series resistors or shunt capacitors can be applied. RC can be applied to the to prove bulletproof the interface side. So and coming to the cable side, definitely filtering and transient protection has to be taken in the cable side. Fiber optics cables can be a better suggestion for the EMI related problems. And the module side, overall the product after the final end product, we can seal whatever you see. And the second thing, filter all the penetrations. That is the thing on the module side. So then actually conductive coating will do the better results. That is a small nickel paint on the plastic will reduce the protection EMI level. That is, it protect the at least 60 dB or more to protect. So vacuum plating or electroless deposition on plastic, it will protect up to 80 dB of the protection. Just a steel or aluminum box can provide 120 dB protection. These are all under the module levels. On the software levels, just a few lines of code will work wonders. That is, for example, a watchdog timer can be concept can be applied to prevent loss of the endless software loop. Software loop can be watched, and some of the components have internal watchdog timer to mitigate the EMI things itself in the component itself. So coming to the solution side, so we have some of the standards available in the industry, so which has to be uh, which is uh, which is defined for the particular situations and particular levels of frequency. So for example, for FCC, it is based on US, so Federal Communication Commissions, and CISPR is based on European thing, International Special Committee for Radio Interference, IEC, International Electrotechnical Commission, and the European Committee for Electrotechnical Standardization. IEEE is Institute of Electrical and Electronics Engineers, and other standards are also available, including ISO, SAC, and which also define the number of standards geared to specific applications or industries for the commercial or industrial products. So, for example, ESD immunity, which defines IEC 61004-2. So, likewise, we have so many numbers of standards available, which are paid uh, standards, which has to be the industry has to be paid for getting the standard. It will be reviewed by the committees, and it will be updated. Revisions will happen. Uh, on the time during the time interval. So we have to be updated in this standards. So while before releasing the product. So up to 202 kilohertz, the harmonic standards limits the emission level very low level. So no major trouble can happen. Over upon 150 kilohertz, to meet the reasonable standards avoids most troubles. So we have to be very careful if the frequency is very high. So these standard committees defines three types of standards. So generic standards, basic standards, and product standards. So basic standards will have only the general considerations, definitions, terms, rules, and guidelines for emissions and immunity testing and test methods. Even for the testing of testing equipment, test equipments have the basic guidelines which have the standards. So which that testing equipment has to be in the this FCC or CISPR defined standards has to be. Then only the calibration they'll be accepted as the for the regulations. So generic standard which has the limits and maximum test levels for a particular product in a particular EMC environment. for which no AMC product standard exists. So it's a generic type. So product standards are limits and maximum test levels for a certain uh, particular product. It's medical, for example, a medical equipment will have the, for medical equipment is different from the commercial ones. So particular product have the particular standards. So this has to be satisfied. So we have high-speed products like e-mobility, like automobile vehicles, smart grid, wearable technology, smart homes and offices, efficient lighting, welfare. So these are all the products which are very sensitive in the thing in the market. So this has to be undergo for the regulations. So regulations means that this CE or FCC that does not have a standard. We have to test the product with the these applicable standards uh, like these standards, CISPR or whatever it may be. So these standards has to be applied and testing of the equipment has to be done initially, and with the test results, we need to apply for the regulations, certifications. So common regulations are different countries follows the different regulations. These are all FCC and triple C, CE, BIS, like some of the examples you can see. So various countries follows various regulations. So if you need to sell the product in Indian product to other countries, you need to follow that regulations definitely. So coming to the text standards, so we have the like already we saw EMC comes split into two things, that is EMI and EMS. In the initial slide we saw. So conductive emission, radiative emission under the emission side. So this is opposite to that of the susceptibility side. So conductive emission is opposite to the susceptibility, conductive susceptibility. Here the emission is actually source. Here the susceptibility is a victim. And radiated emission is similarly, radiated emission is also opposite to the radiated susceptibility. So these are all the IEC CISPR standards, 11, 14 and 15, CISPR 32 or different standards for the radiated emission and conducted emission we need to follow. To getting this standards, we need to pay for the IEC CISPR. Uh, and for each number specifies one thing. So this is actually maybe this 11 for the industry and 14 for the medical and 15 for the other specific product. Like, so we need to that has to be before giving to the testing. We need to have the clear idea of which standard has to be tested for the product. And for the radiated conductor susceptibility, it is IEC 61004-6, and radiated susceptibility IEC 61004-3. So coming to the measurement side, so it can be done through simulations. Before actual measurement can be done through simulations. So there are three types of simulations are available. Simulators are available. One is electromagnetic simulator, which solves purely on Maxwell's equations and simulate the electrical and magnetic fields with in frequency or time domains, whatever. So these are the full wave simulators, and the circuit simulators which solves the using Kirchhoff's voltage law and current law, like MATLAB and other SPICE and other things. So we need to have some equivalent circuits and equivalent knowledge of the circuit knowledge of the circuit. And behavioral simulators, which is the more abstract level simulators. So coming to the EM simulators level, that is electromagnetic simulators, full wave simulators, Maxwell's equations solution. We have many tools, market commercial tools available. Power SI, Power SI Wave, CST, and soft. So these are all the hyperlinks. Also, EM Pro is HFSS. So various high-end EDA providers are providing the tools for the simulation part. So what we do for the EM simulations? So we'll see only for the EM simulations. So EM simulation side, we just need to import the CAD data or EDA tools, EDA files from the into the simulators, EM simulators. and we need to tag or we need to identify the which net has to be simulated or modeled for the simulation. So critical components has to be modeled, and anyway, before coming to the simulation part, we have designed we should follow the design strategies as discussed earlier. It has to be done, and after the part only we are coming to the simulation side. So this full wave simulators definitely helps to fill in the gray areas. So so we need to model and run the simulations based on time domain or frequency domain, whatever we want to do. This previous slide explains the software solutions. How as a software you can design, and if the results doesn't meet, you can iterate the design process. So again, after designing, after coming to the thing, hardware solutions. As a hardware solutions, we can have fabric over foam, shielding, coaxial transmission line method, and dual TEM method, rectangular waveguide method, nested reverberation chamber method, shielding box method, shielding room method, free space method, and electrically conductive filters applied for CM and common mode and differential mode noise, ferrite application of ferrite, grounding, bonding, spatial placements of hardware, circuit topology modifications, and spread spectrum, etc. These are all the hardware solutions available. For the system level, you can have, as discussed in the previous thing, we can have the optimized code. The advantage is there is no impact on the physical redesign of the system. So as much as possible, we can solve in the system level solutions and design level solutions. After that, we can go for the hardware solutions. And coming to the EMC precautions in the design stage, converter topology analysis has to be done, and cabling control, that is the main factor, and risk of oscillators, immunity testing has to be done. So we'll see in brief what are all the precautions side the design stage. So application of hot conductor. Actually, hot conductor is a piece of circuit submitted to high voltage, high dV by dt or high di by dt component. So our aim is to mitigate, to reduce the dV by dt and di by dt component. So for that, application of hot conductor can be, which will suppressing the localized capacitor, floating hot sinks, heat sinks, increased distance to chassis ground, adding electrostatic shields connected to the DC bus. Like so, they're definitely using the bus bars, sandwich structures, reducing the size of the loops must improve the quality. So equipotential here, it means the impedance matching criteria. So definitely this will give the proper. So external cable side, all we discussed. As we discussed, EMI mode filter or external unshielded cable. This will be the filter with the correct structure has to be installed. For instance, without saturated chokes has to be implied. Then all the filters should be directly connected to the same ground. That is the main point to limit the. This is to limit the common emission and to control the crosstalk. So that has to be done on the external cable side. So oscillators, risk of oscillators will be increase with the dV by dt and di by dt in switching rate. So oscillators has to be taken care. So need for EMI input filter. So as of now, we saw the PCB level filters, that is PCB level design strategies. So need of filters has to be, anyway we need to have some external filters to safeguard the product. So after the internal filter, external filters is also necessity. So suppress the emissions, and again the same coupling path is in make the coupling path as inactive and make the receiver as less vulnerable to the emission. So main thing is good design of EMI filter must satisfy the EMC standards. So coming to the summary side, EMC comprises of series of related disciplines like characterizing the threat, setting the standard for emission and susceptibility levels, design for standard compliances, testing for standard compliances. So definitely the problem of understanding is required for the interference of source and signals is required, coupling path with the victim, nature with the victim also is this required. So based on this thing, we have to have the power converter system. So coming to the testing side, so we just measure and this is actually actual testing side, so product testing side. So why do we need to test the product? So to make sure the reliability, to prevent the rework. We are testing the prototype only. So to prevent the rework, it will be testing will be helpful, and to avoid the potential hazardness, to meet the regulatory requirements, to improve the performance of the product, to reduce the risk of the costly non-compliance, to strengthen your competitive position. That is very important to survive in the market, and to safeguard the sensitive analog and RF circuitry, and subsequently calculating the ESD levels. So this is a must thing. So for these purposes, we need definitely a real-time testing. That is prototype testing. EMC test compliances can happen in two ways. That is intra-system EMC. This is for stable operation performance quality. Inter-system EMC for protection and safety from the danger side. So these have the regulations and certifications are there. So this slide actually is an overall view of the product test plan. So after completing the product, what we have to do, the material durability test and product specific test has to be done, and characteristic test. So under the characteristic test only, our EMI-EMC test are coming. So under the characteristic test, we have some other general performance, environmental test, safety test. So another one is the electromagnetic compatibility. So where we have seen these four: conductive immunity, radiated immunity, that is susceptibility, and conducted emission and radiated emissions we have seen. So other type of tests are transient test, that is ESD for ESD, burst, voltage dips, surge, and magnetic field. Another one is telecom test. So this slide shows the EUT under test. So EUT is the equipment under test. That is our product will be placed under the either as a source or as a victim. So it has to be test for emission as well as the immunity. So for the radiated immunity, we have seen these are all the various things. This is actually this is a specific product. So depending upon your application, or depending upon your product, this this standard will be number will be varied. So this has to be properly selected. So testing setup can be so this EUT, this can be placed in the ground, or above the ground level. So this depending upon where your EUT is will be installed in the industry or your commercial application. So based on the application, you can place the EUT, and it can be connected with the AC mains with the coupling clamps. That is, we have to inject the, in case of immunity, we have to inject the field, or in case of emission, we have to measure the field. So setup may be a little different for the emission and immunity side, that is susceptibility side. So but that EUT will be under in the chamber of thing. So these are all the typical EMC test facility is available. So this is a 3-meter EMI chamber. So where the device is placed here, this is connect power and other connections will be 3 meters away from the tip. So this is a 30-meter EMI chamber. Here this is a shielded room. This is the RS chamber. This is a OATS. It is open air test site. In case of defense and other things, it has to be tested in the open site. These chambers are the ideal scenario. This open air will be the practical scenario. So, depending upon the product that you install, it has to be taken into this whatever the chamber is required. This is a 10-meter chamber. This is a typical semi-anoic chamber. So here, see this the product can be placed above the top of the ground. So there will be inside the product that will be, I mean, inside the chamber there will be antenna to emit the interference. That is radiated. It can be direct or indirect. Direct means it will be in the through wires it will be connected. Indirect susceptibility, it is to be transferred through the antenna. Radiative waves are passed to the EUT and measure how it performs for these situations, the electromagnetic wave situations. For that, various for measuring the test results, there are various equipments are available. EMI receivers and some of the transducers, PDN, and other are available for the testing the instruments, and it can be manipulated with the help of software or correlated testing, and can be taken as a report, which has to be given to the EMC EMI regulations. Regulations means that it's BS, for example, BIS, FCC, CE, like uh, for the certification process. This is a typical EMS RS chamber. It is our radiated susceptibility. This is standards mentioned here. This is a typical open area test sites. So here probably these test sites will be in the hill area or other remote areas only, as there will not be any mobile towers and other areas. So this will be a remote location where the open area test sites has to be conducted. So coming to the as we see already, so radiated emission. These are all the EMC tests. So I'm going to give some of the standards related to these tests. So related to radiated emission, this is the frequency level and 30 megahertz to 1 megahertz, 1 gigahertz. Standards are 6 per 11, 12, 13, 25, 22. And major testing systems refers to testing systems, that is test equipment refers to CISPR system. CISPR system defines the testing system standards. So test facilities are these are the test facilities available, has to be done in the thing. And test equipment are EMI receivers, spectrum analyzer, test antenna can be loop, dipole, log, periodic, bicanal, and other things, and others. You can turnable antenna master, like etc. These are all the limits of the test emission test. Test for the conducted emission. Emission side. So up to 30 megahertz, we can follow the conducted emission from 150 kilohertz to 30 megahertz. So test standards available are CISPR 11, 13, 14, 15, 25, 22. So test system, again the measurement test instruments standards are presenting CISPR 16, and test facilities are shielded room, adequate ground planes is enough. That or just an adequate ground plane is enough. Test equipment are EMI receiver. These are all the measurement tools. There is EMI receiver, spectrum analyzer, and others LISN. That is LISN is a line impedance stabilization. It's a transducer typically designed to allow the for measurements of electromagnetic interference existing in the power line. So this is the limitations of the CE. This is test for radiated susceptibility. So radiated susceptibility in the frequency range of 80 megahertz to 1000 megahertz. So this is the immunity of the immunity check. So test condition can be 1 to 30 volt per meter, and standards IEC 1610004-3 and ISO 11452-2. Test facilities are there, and test equipments, power amplifiers and antenna, field probe sensors, signal generators, directional coupler and power meters. Others, test software for manipulating the thing. So, for example, this software, if you are calculating for a particular 3-meter immunity, so it will calculate for 30 meters immunity. So that correlation can happen through the test software. Test for conductor susceptibility in the range of 150 kilohertz to 80 megahertz. So the test conditions can be 1 volt to 30, 100, 10 volts. Test standards are again IEC 61004-6, and test systems are shielded rooms. Test equipments are power amplifier system, signal generator, directional coupler, power meter, CDN, current clamp. So these things are injecting the noise into the intentional noise are injected to the EUT, that is equipment test for the immunity purpose, testing purpose. So others test software is required to calibrate the or to correlate the results. So finally, the electrostatic discharge. This is a very serious test, has to be taken care. So test conditions are 8 kilovolt. So in the air discharge and 4 kilovolt in the contact discharge. This contact discharge is actually the probe has to be touched to the equipment under these conditions. And air discharge is discharge through indirect method, that is air through air medium in the chamber itself. So standards followed are IEC 61004-2 and ISO 10605. So test under the test system test facilities are shielded room. So some of the labs, some of the industries might not have this much facilities the test labs. So for that case, some small GTM chambers are available. So that will help us the industry to for testing the same to getting the same results. But the test labs are preferred for the perfect results. So only on normally we say that is not every product will undergo complete gives the complete results EMI test. So only 50% of the products will pass through the test. So again remaining parts has to be redesigned or iterated in the design stage, or other filter sites has to be done and modified, and after that testing has to be done. So these are all the testing side, actual testing side. So in the simulation tools, we'll have the ideal scenario of the EM wave propagation or EM wave issues. So in the test, actually, in the actual test, is actually a practical scenario. So there may be 80% 80% of the matches can happen. So remaining 20% will be maybe a mismatch between the actual scenario and the ideal scenario with the actual testing methods. So I have shown some of the testing instruments. So these instruments are manufactured with the standards of CISPR 16. So without that the testing regulations, they will not certify the product. So it has to be measured upon the standard measurement tools only. So these are all the EMI test receivers, oscilloscopes, and ESD generator, and spectrum analyzer, LISN, signal generator, surge generator, antenna. So there are different antennas are available for the immunity test purpose, and network analyzer. So above equipments are the most commonly used available for performing the EMC measurements. And last but not the least, these we have seen many EMI-EMC problems, which the extensive researchers are going on the issues due to the EMI effects on the human body. So this definitely affects the organ and tissues. So some of the researchers we found that found that this EMC issues will directly affect the bone marrow. So that will cause the leukemia, that is the blood cancer or the bone related issues. So and not only that, it will affect the nervous systems, visual systems, and immune systems, and lot more. So these are all the tested with the guinea pig or rabbits with the with animals and everything. It is proven. So under the EMC, this electromagnetic will affect the human. So we have to safeguard our lives, which is very important. So because of that, we as engineers we need to fix the EMC or mitigate the EMC part, and as much as possible, we have to be away from the EMC environment, EMI environment. So with this, I conclude the presentation. This is the overview only. This is actually a ocean. Each area it goes on with a very vast thing, so which is not available in the curriculum. So so if you have interest, you can explore your things in the individual fields. So so that's all from my side. So thank you for patience listening, and any comments or any questions from your side.
Thank you, ma'am. We'll wait for the participants' questions. Any questions, participants can post in the chat box.
I hope everyone are okay with the presentation. So I don't find any. Uh,
Uh,
so thank
Presentation
you.
was very informative, and thank you very much for accepting our invitation and
Okay, thank
spending your valuable time with us, and for sharing your experience and expertise in the area of EMI-EMC, because uh, we don't deal much in this area in the academic side. So
yes.
it was very useful session. Thank you very much, ma'am. Because this EMI-EMC also is very important, most important, I would say. But we hardly touch these topics in academic side. So thank you very much, ma'am. Ma'am, one question in the chat box. What are the softwares that can be used for PCB designing?
Uh, for the PCB designing, there are many high-end tools are available and low-end tools are available, and some of the open source tools are available. So, depending upon your, if you are working for academic projects or academic side, you don't need to purchase with the high-end products. So, you can have some open source product like. I find the design spark is very useful, which has all the features exactly with the high-end product. So Design Spark is it's a European-based product which has a schematic editor and a PCB editor. So you can use the tool for designing your PCBs. So other than that, some of the open source tools are also available. So you can maybe you as because you are in a university or academic versions are also available with the maybe in the limited cost edition. So you can get whatever. So for the open source, I prefer personally designs part.
Any other questions from the participants? I guess there are no more questions, ma'am.
Okay.
Thank you very
Okay.
much, ma'am.
Thank you for inviting me to share my views on EMI-EMC thing. So this is a nice medium to share my views. So thank you so much for inviting
Thank
me
you.
for the session. Thank you.
Thank you, ma'am. Thank you, ma'am. Thank you so much.
Thank you.
For the participants, tomorrow, as usual, we have session 1 and session 2, and afternoon at 2, you'll be having the test. So during the session 3, so we don't have the session 3, so during that time, you will be having a test. So more details about that, we will share it in the WhatsApp group. Thank you all. Thank you.